Assalamualaikum and a very good day to Dr. Hadi. Welcome to our forum presentation. Our topic today is soil improvement and stabilisation techniques. Soil plays a very important role in every construction project because it supports buildings, roads, bridges, and other infrastructure. However, not all soil has the strength and stability needed for construction. Weak soil can lead to problems such as excessive settlement, slope failure, and even structural damage if it is not properly treated. In today's discussion, my group and I will explain the different soil improvement and stabilization technique, their application, and two mentioned case studies that show how these methods are used in real construction projects. So now, to help us understand this topic in more detail, I had like to welcome our first member, Nur Alihat Fina, or as she's commonly known as Fina. Welcome Fina, it's great to have you with us today. So, the first question is, why is this process so important? What could happen if engineers skip soil improvement before starting a construction project?
So that's a great question. So soil is the foundation of every structure. So if the soil is weak, the building may experience excessive settlement, crack, or even structural failure. So poor soil condition can also increase maintenance costs and shorten the lifespan of a building. So by carrying out soil improvement, engineers can ensure that the ground is strong enough to safely support the structure for many years.
I see. So, before selecting a soil stabilization method, what factors do engineers usually consider?
So there are several important factors. So the first factor is soil condition. So it is because different soils require different treatment methods. For example, clay soil. So it usually stabilized using lime, while sandy soil is often improved through compaction. So that the second factor is loading requirement. So engineers need to know how much load the building will transfer to the ground, and then heavy structures such as high-rise building or bridges require stronger ground improvement compared to the smaller buildings. So another important consideration is the settlement criteria. So engineer must make sure that the soil will not settle excessively after construction because uneven settlement can damage the structure. So lastly, they also evaluate the groundwater condition. High groundwater level can reduce soil strength and affect the effectiveness of certain stabilization methods. So especially chemical stabilization. So in some cases, drainage or dewatering system are required before the treatment is carried out.
Oh, that's very interesting. We have also learned that there are different types of soil stabilization method. Could you briefly explain the main classifications?
Of course, there are three main classifications. So the first is mechanical stabilization, which improves soil through physical methods such as compaction. So these increase soil density and bearing capacity without changing its chemical properties. So the second is chemical stabilization. So where material like cement or lime are mixed into the soil, then this material react with the soil and make it stronger, more durable, and less affected by water. Fourth is reinforcement stabilization, which uses material such as geotextile and geogrid to strengthen the soil. This material help distribute loads evenly and improve the stability of weak ground. So each method has its own advantages, and engineers select the most suitable on one based on the site soil condition and project requirements.
Beside the method themselves, what material, equipment, and testing are commonly used to ensure the stabilization work is successful?
So common stabilizing material include cement, fly ash, and other industrial byproducts. So depending on the method used, contractor may use roller, compactor, excavator, soil mixing machine, or deep mixing rig. So after the work completed, geotechnical tests such as moisture content test, compaction test, California Berry Ratio test, and unconfined compressive strength tests are carried out. So these tests help engineers confirm that the treated soil meets the required strength and quality standard before construction continues.
Thank you, Fina. That was a very clear explanation of the basic concept, design consideration, classification, materials, and testing involved in soil improvement and stabilization. Now, let's moving on to the practical application through two real construction projects in Malaysia. Joining me for this discussion are two members. First, we have Kashful, who will explain our first case study, which is IKEA Batu Kawan in Penang. And next, we have Adina, who will present our second case study, Pavilion Bukit Jalil in Kuala Lumpur. Welcome, Kashful and Adina. Thank you for joining today's discussion.
Thank you, moderator. We studied the IKEA Batu Kawan project in Penang. The main challenge there was natural marine clay. This type of soil is extremely soft, weak, and squishy. If you build a heavy commercial building on it without treating the ground first, the soil will sink heavily and cause the structure to crack or fail.
To contrast that, Pavilion Bukit Jalil in Kuala Lumpur dealt with a completely different nightmare, that is, an old tin mining site. Instead of uniform clay, the ground there consists of mine tailings. This is a very unpredictable and loose mix of sand, sleet, and a pocket of soft mining slime with a very weak SPT and value that is below 5 to 10.
Okay, so we have soft coastal clay in Penang versus unpredictable mining slime in KL. How did the engineering solution differ for these two places?
For IKEA Batu Kawan, the team chose a mechanical method called vibro replacement stone columns. They lower a heavy vibrating probe into the ground to push the clay aside and make deep holes. Then they fill the holes with coarse crushed stone 20 mm to 75 mm and compacted them layer by layer. These dense stone pillars reinforce the weak ground mechanically, increasing its strength and helping underground water drain out faster so the soil settles quickly.
Meanwhile, simple mechanical compaction would not work on the soft mining slab at Pavilion. So they will use a chemical method instead called deep soil mixing. A special drilling rig bored into the ground and injected a cement slurry, mixing it directly with the loose soil using a rotating blade. When this cured, it hardened into a solid soil cement column that made the ground strength uniform across the whole site.
Oh, that is an excellent comparison. Using stone pillars to mechanically reinforce clay versus using cement to chemically harden mining slime. What were the financial and management lessons from this project?
For the IKEA project, using local crushed stone kept the ground treatment highly economical for such a large open area. However, a management lesson came from a human error where a roof beam was set at the wrong level during superstructure works. This simple mistake resulted in non-conformance report that cost up to 50,000. Means to fit using specialized curing brick. This proved that foundation success means nothing if the team lost focus during the later construction phases.
Over at Pavilion Bukit Jalil, the financial scale was much larger because they had a basement and massive retail load. They had to combine the DSM method with huge deep board piles and contiguous board pile retaining wall to keep the excavation wall from collapsing. This heavy foundation work pushed the infrastructure costs up to an estimated RM 1.9 to RM 2.1 billion. To balance the budget, engineers used post-tension steel tendons for the upper floor to create a long span with fewer concrete columns, saving material costs up top.
Thank you, Kashful and Adina, for that excellent breakdown of our two physical case study. It is clear that choosing between mechanical and chemical method depends entirely on the unique challenges of the site. To help us compare these two projects deeper, let us welcome our next member, which is Auni Khairia. Welcome, Auni. Let us start with what the engineers had to think about first when designing this foundation.
Thank you, Awati. The design goal for both projects were completely different. For IKEA Batu Kawan, the main focus was transferring heavy building loads safely into the using stone column. But for Pavilion Bukit Jambi, they had to stabilize losing mining line and handle a high water table using cement mixing to stop the ground from shifting or collapsing.
Yes, the type of soil completely dictates the engineer approach. What about the materials they use on site?
Okay, for the metal selection, play a huge role in both performance and cost. For the mechanical piece of IKEA, they rely on polished stone, which are naturally stable and they don't underground damage. For the telephone piece of heavy one, they use a heavy cement slurry injected directly into the ground to bind the shop, with mining slime together.
It is interesting how one relies on raw stone while the other uses a chemical cement mix. How about the heavy construction machinery and processes?
So the machinery used show how different the two methods are. IKEA Butukawan require heavy vibrating probes and frames to mechanically push the clay aside and pack the stone lightly. Pavilion Bukit Jalil, on the other hand, need specialized drilling rig with large rotating blade to mix the cement slurry directly with the soft soil in the ground.
Both methods clearly require highly specialized equipment. Finally, how did they test the ground to make sure it was safe to build on?
So for the testing, it's critical for quality control. At the IKEA site, they use digital monitoring during installation and verify the soil final strength using standard penetration tests. At Pavilion, because they use a chemical cement mix, they had to run continuous concrete cube tests and column integrity tests to confirm that the hidden foundation block reached their target strength before building the heavy soffit.
Thank you, Auni. That makes the differences so easy to understand. It shows that both methods are highly effective when matched with the right soil conditions. To conclude our forum today, choosing between mechanical and chemical soil stabilization is not about finding the best overall method, but finding the right match for the site. As we saw, mechanical stone columns are the perfect, cost-effective choice for natural, soft coastal clay. On the other hand, chemical deep soil mixing is essential when dealing with unpredictable, loose, mine tailing and high water tables. As future quantity surveyor and construction professionals, understanding this technique helps us balance engineering safety with cost optimization from the very start. We hope this session has provided clear insight into how ground improvement shapes successful in project in Malaysia. Thank you to all our brilliant members and thank you to Dr. Abdul Hadi for tuning in. See you next time.